the important things in this particular lecture is LC oscillations and transformer. So what basically we are going to discuss, like in the previous class we done all the things of LCR, but still in a great detail, resonant circuit, or you can say resonance condition for a LCR circuit. Then what a LC oscillation is, like you have seen the oscillation in spring pendulum case, or you can see in a in spring or mass case, or in pendulum case. In a same analogy, we going to see this particular oscillation here as well. Okay, then we are going to switch into the transformer. So the derivation of transformer, turn ratio, voltage ratio, current ratio, that thing we are going to discover, or that thing we are going to discuss earlier. There is the third student also, but I think he is in the lobby. Pavan Aditya, beta, you just do one thing. Leave this session and join again, because you are not visible to me. Okay, is this clear? Is it clear, beta? Good. So the basic thing, when we start from the, like we already done, this is your resonance of a LCR circuit. So what a LCR circuit? In any particular circuit in which we apply this particular, wait a minute, I need to do this. In a particular circuit in which we apply a alternating voltage, L, C and R. L stands for inductance, C stands for capacitance, and R stands for resistance. In a series, that particular circuit is known as LCR. This symbol, this sign is basically shown to you, that is your alternating voltage. So this is some alternating voltage, okay, and the current is going in this way. This is your resistance R, this is your capacitance C, and that is your inductance L. We discussed this particular thing in a great detail in the previous class. Okay, so what is the resonance of LCR circuit? We discovered that the amplitudes of voltage, frequency and current are related to each other in the following series of LCR circuit, where IM is basically the maximum or peak value of a current is Vm by Z. Z is basically the net impedance. Okay, Z here is total impedance, and impedance is what? Impedance is basically a kind of a resistance. So that is R square plus XL minus XC square. Whole square. So here we need to write XL. Wait a minute, I need to remove this, and that is XL minus of XC in the same fashion, omega C, basically omega L minus of, wait a minute, I need to remove this one also, the whole thing. Yeah, so that is your R square plus 1 upon XL is basically omega L minus 1 upon omega C to the power 2. Okay, and that everything lie under the what particular is, this is everything in the denominator. Clear? So that is your Z, where XC is equals to 1 by omega C, XL is omega L. That is not in the subscript, that is in the this omega L, and here C is also in this way. Is this clear, everyone? So that thing we done in the previous class, right? So what is a resonance circuit? The resonance circuit is a kind of a circuit in which the resistance is minimum, and when resistance is going to be minimum, where omega L equals to omega C, or you can say XC equals to XL. So a particular condition when the circuit impedance is low, first of all, as a note you can find it down, the first point, the circuit impedance is low, the current flowing through is at its maximum to accomplish. So we have that, so we change the frequency value till we have. So there are 2-3 conditions for a resonance circuit. Separately I write it down here. Conditions for resonant, or you can say resonance, resonant series LCR circuit. Series LCR circuit. So the basic conditions somewhere written like this, and instead of resonant circuit you can find these words or these lines also to identify that particular circuit is a resonant circuit. Is this clear, everyone? So the first basic condition is resistance, or you can, instead of resistance, total impedance, total impedance, total impedance Z equals to Z is low or purely resistive. Either you resistive, wait a minute, purely resistive. Either you, either you see this particular line, the total impedance Z is low or purely resistive. What is the meaning of saying that? Z equals to R only. Is this clear? So this is your first condition. What is the second condition? I mean, you know all the condition. The main thing is I'm just rewriting in the sentences, like another sentences, instead of directly writing this thing, resonant series LCR. The second thing is current, or you can say peak current. Peak current IM, which is Vm by Z equals to Vm by R, is maximum. Vm by R is maximum. Maximum in this case. Or you can say just maximum. Maximum. Okay. The third main condition is tuning the frequency, or you can say tuning the frequency of alternating voltage, tuning the frequency, tuning the frequency of alternating voltage till we get XL equals to XC, where XL, you know, impedance on an inductor, where XL is omega L, or XC is 1 by omega C, where omega is 2 pi F. Is this clear? So these are the three different namings or lines, or you can say conditions for a resonance series LCR circuit. Clear? And that is written over here also. Like the first condition is this, and the second condition is written over here. Change the frequency value till we have X equals to XL at a given frequency, which is omega naught, and the impedance, which is Z equals to R. So this is your third condition. Either you can write low, either you can write purely resistive. Purely resistive. Okay, this is your purely resistive. And current is maximum is written over here also. Is this clear, everyone? So, or you can see that instead of 1, 2, 3, wait. These three conditions are like this. You can write this one your first condition, the frequency thing. This is your purely resistive or resistance or total impedance is low, second condition. And the third condition is current is maximum. I can write in a different order. The same thing is written over here. I just make this thing in a clear separate way. Is this clear, everyone? What is going on here? Clear na beta? Dharneshwar, Kyle, Netra, just open your cameras too. Okay, so that is, I give you a hint in the previous class, but this is the detailed example, or you can say detailed explanation. Clear beta? Shrutika, Vishwanath, both of you. Okay. So then when the series LCR circuit impedance, Z equals to R equals the resistance, this frequency omega naught is referred to as the circuit resonant frequency. So this is important also. Even I explained this thing also. So this omega naught is known as resonance frequency. Resonance frequency. REUENCY. Okay, resonance frequency. Or 1 by omega naught C equals to omega naught L, omega naught equals to 1 by LC. So resonance occurs in a series LCR circuit when the capacitive reactance are equal in magnitude but 180-degree apart in the phase. Okay, means this omega XC equals to XL, but they are 180-degree in phase difference. So this is your omega naught is a resonance frequency, important one also. Clear? So that is, wait, yeah, this is done. Resonance of LCR circuit. For the series LCR circuit, the phase difference phi equals to tan inverse XC minus XL minus XC equals to R. So either you can write XC minus XL or either you can write XL minus XC. For XC equals to XL, which is impedance on capacitor, impedance on inductor. So phi is 0. So this is also you can understand in this way. For phi equals to 0, for phase difference phi equals to 0, it shows us the circuit, the LCR circuit is the series LCR circuit, the series LCR circuit is in resonant condition, is resonant condition. So you can understand in this way also. Okay, or XC greater than XL, phi less than 0, the circuit is predominantly capacitive. Means if your X is greater than XL, so obviously it is dominating towards the capacitance. It is dominating towards the capacitance. So you can say that predominative capacitive. Or if X is less than XL, so phi going to greater than 0, and then the circuit is predominatively inductive. Or you can rewrite this thing also. This is XL minus XC divided by R. Okay, is this clear, everyone? Okay, what do you get from this resonance circuit? In last class, we are talking about resonance. What is the meaning of this resonance circuit? Tell me, anyone. What physics you get from this? Why we are discussing this thing since last phenomenon? Tell me. Why we are discussing about that so much? Tell me, beta. If you know so, and if you don't know, then why don't you ask? And what is the role for this? I teach in the previous class also. I started this class also. What is the significance? Whenever I say physical significance of this particular thing, of this particular topic, means I just want to know about the physics. We trying to discuss about the main physics behind that. It's okay, beta. Okay. So tell me if anyone know physical significance, and if you don't know, then why don't you ask? Physical significance of resonant series LCR circuit. Tell me. Tell me, anyone. Tell me, beta. Parikshit, Kayal, Shrutika, or this Dharmeshwar or Dameshwar. Tell me, beta. Physical significance. Do you know what it is? If you don't know, so just write right here. We don't know, sir. So I can teach you quickly. Do that. Everyone. Akash Karan also. Kanna. Beta, why are you not visible, Pavan or Akash, in the this feedback? I mean, why cannot I see you? At least write this thing. Everyone. Everyone, go ahead. And if you know, so let me know. Physical significance, whenever I ask this thing, physical significance of momentum, physical significance of vector, physical significance of vector field, physical significance of this, what I'm writing right now, means you just need to tell me the physics behind that, not mathematics, not formula, nothing else. Tell me. You know, Shrutika, Hari Mahesh, did you know the physical significance of LCR circuit or resonant series LCR circuit? Okay, did you know what is a resonant series LCR circuit? I'm not familiar with it, sir. Okay, first of all, resonant or resonance of a LCR circuit is LCR circuit, you know, in which XL equals to XC. This thing, this particular condition is known as resonance. So the two important physical significance and the power loss is very okay. Power loss is less. First, now from where it comes, as you can see, power equals to VI, right? V is maximum, I is maximum. Here, na? Because V is Vm here, sine omega t and so and so. And I is Vm by R, sine omega t obviously. So I becomes Im, sine omega t. So in the circuit itself, I cannot lose power because only I have one component, resistance. Because X equals to XL. So the impedance on this particular thing, which is a capacitor, the impedance on, you can say, this particular thing, which is a inductor, is cancel each other. Isn't it the X equals to XL? So my total impedance Z becomes R. In this case, I get the maximum power. So I cannot lose power more on components itself. What are the components? LCR. For the LCR circuit, okay, here you can see that. For a LCR circuit, wait, I can copy this. Yeah, just a minute. Give a minute. For a LCR circuit, this is my LCR circuit. Just a minute. Okay. Yeah. So this is my LCR circuit. Clear? So in this LCR circuit, as you can see, this is your voltage, this is your resistance, this is your capacitance, this is your inductance. So I cannot lose power in this because it is a series LCR. So here we have voltage which is VC. Here we have voltage which is VL. Here we have voltage which is VL. Clear? Because in series, voltage is divided. So when voltage divides, so power is going to be divided also because power is VI. So I lose very less power in this circuit. So that is why I read about it. Clear? the power in, or you can say energy basically, uh, energy, because if you know the energy, you can know the power also. Okay, because basic thing, power equals to energy upon time taken. Clear? And how much you work do in a particular time period. So this is your power. So if you know energy, you can know the power also. So energy on capacitor. Energy on capacitor is UC equals to half UV half CV square. And if you know this formula, Q equals to CV, so V equals to Q by C. So 1 by Q square by C. So this is my energy on capacitor. In a same sense, energy on inductor is half Li square. Clear? So when power is less, or you can say when power loss is very less in this particular circuit, so energy loss is going to be very less, because there is the role for C and L is neglected here. So these energy are not going to be converted into any particular energy. The maximum amount of current I can get. So this is your first thing, very important thing. The second thing is written in the condition also. Get maximum current. Maximum current. So what is the use of that? Whenever I make any particular circuit, I tuned the frequency of a component in that particular such a way so XC cancel XL, and that particular LCR circuit behave like a resonant circuit. And I can get the maximum current and minimum impedance. If I get the minimum impedance, so I can get the maximum current, maximum power, less energy loss, less power loss, everything. That is why we are focusing on this. Is this clear? Clear? And there is a one graph also, somehow look like this. Just a minute. So what it is? This is your resonance graph. Means energy or the power is going to be maximum. This is your power. This is your frequency. At which particular condition? F naught. What is F naught? F naught here is resonance frequency. Got it? Below, or you can say before this resonance frequency and after this resonance frequency, you cannot get the maximum power. Why? So because power is going to be lost at particular components at C, at L. And what is the power? Energy upon time. So what is energy? This C. The 1 by 2 QV, 1 by 2 CV square, 1 by 2 Q square by C, or half Li square. Clear enough? So that is the physical meaning, physical significance. That's why we are focusing on this thing a lot since last class. So if you read something, if you learn anything new, so ask this thing, like why we are doing this. Since last class, I am just telling you resonance. What is the basic use? Why we are giving so much importance to that particular topic? Every particular topic is not just for gaining the marks. See, learn one thing. If you learn, like everyone, I can see that, I mean, you are that particular age group. So if you don't watch the particular movie, Three Idiots, watch it right now. I'm not saying open any particular refrigerator or the components or electrical components in your home, but the best, you can say, moral of this particular story, that particular picture is learn to gain knowledge, not to gain marks, right? Once you started thinking in this way, I need to learn this thing to know what I mean, to know what this is going to be used for, to know what is the basic science, basic physics, basic chemistry, basic mathematics is behind that particular topic, subtopic. Clear na? Or specifically in physics, we don't teach you anything. If I'm saying anything means anything which is not going to be used for you. Neither the scientists, neither the teachers, neither you have that maximum, you can say, amount of time. So we just teach you something like which is not going to be used for you. Okay. So in any particular case, if you are trying to invent, you are trying to make any particular devices in which obviously there is so much electricity. So if you suppose try to make an engine, okay, but instead of a big electrical engine, you try to make small engines and then added in this particular series or added in a parallel. So your voltage remains constant and you get the maximum power. So in this particular scenario, you need to know these basics. Like why should I just need to make at the resonance circuit? Why not any other? Because at this particular frequency, I get the maximum power. And when you get the maximum power, you can turn this particular power, you can turn this particular energy, because power is energy per unit time, into any other form of energies also. Motional energy, electrical energy, or heating energy. Clear? That is the thing. Okay. Moving ahead. This is done. Yeah. Definition of Q factor. This already we defined that, but again, after knowing the resonance and sharpness of a resonance, so this is known as sharpness of a resonance. This thing. How much it is sharp. Okay. If it is not sharp, so it means there is a maximum range. If it is sharp, so it means at single particular frequency you can get the maximum power. Let us help you understand Q factor and its use. So Q factor stands for the quality factor first of all. Okay, quality factor, it does not have any dimensions. It is used to characterize the center frequency. Center frequency is that particular. Okay, I can give you few names. This is your center frequency. Or should I make on this page? Wait, I can make here. Or just I give you a diagram also. Wait for a while. Resonance frequency. Best picture I can find. Just a minute, beta. Is it visible to each and everyone, right? So this is your frequency formula, and this is I make the in the last page also. This is circuit current. This is frequency. You can draw the current. You can draw the power or voltage also. This is I max, which is V by R. This is I upon ZC. What is this? Means before this. Before this, yes, sir. I mean before this, the circuit behave as a capacitive circuit. After this resonance frequency, the circuit behave as a inductive circuit. So that is why I write ZL. That is why I write ZC. FR is the series resonance frequency, or you can write F naught. So quality, what is now here? Bandwidth. This is your bandwidth. Okay, this one is bandwidth here. That is why I give it to you this diagram. And center frequency, this is your center frequency. This one. This one is your center frequency. Is this clear, everyone? Of the resonant and underdamped resonator. Underdamped, full damped, you don't need to worry about it. That is a little high concept. So it represents mathematically, what is it represents? Quality factor Q restore upon lost per cycle. Means for a RF resonant circuit, RF means resistive frequency resonant circuit, the Q factor is given this F naught upon F3 dB. Okay, dB is bandwidth here. and another way, this is your resonance of a circuit. Is this clear? Quality factor in this previous class, I can give you Q, which is R upon Z. So there is one quality factor. Or here, this is R, restore lost per cycle, means how much energy, how much power you can restore, or how much you can lost per cycle. What is a cycle means? Cycle means, as you know, whenever there is a, you can say a coil is rotating. So due to coil rotation, due to induced EMF formula, we can generate the alternating voltage or we can generate the alternating current. So in both the sense, this alternating form of voltage or current can be generated by this omega. Okay. Omega means this, according to the cycle, we can find it down this. So that is loss per cycle. Is this clear, everyone? This particular definition and so and so. So that is important also. Like it gives you how much quality of this particular circuit of yours have. Clear, everyone? Clear na? Good. Moving ahead. This is circuit power factor. Okay, this is power factor, not quality factor. Okay, so power factor, the ratio of a active power total power is used to define the power factor of a AC circuit. Power factor cos phi is active power upon total power, which is I square R divided by I square Z. I square cancel each other. So this is your cos phi. Cos phi is a power factor. Okay, so this is important also. Mathematically also or physically means how much resistance you have as compared to the total impedance of a circuit. So that is known as your power factor. Is this clear, everyone? Means how much in factorization you get the power whenever you apply this particular alternating voltage or current, alternating voltage to any particular circuit. Is this clear, everyone? Like in this, how you can understand, suppose like how much you know efficiency. What is efficiency? In previous class, you know efficiency of an engine, right? You hear this term? Efficiency, CIENCY, right? Efficiency of an engine. So efficiency of engine is output power, or you can say output upon input. Output upon input. Or you can say output heat energy to the input heat energy, if we are talking about heat engine. So in the same way, how much output we get, how much input power we apply, that is I square RZ, I square Z and I square R. Because at resonance circuit, this is my output power I get, because I tuned this particular frequency in that manner. So after applying this particular voltage, I can get only power at resistance. But initially we have to deliver the power on the whole circuit. So that is your, in a same sense, factor, or you can say factorization, circuit power factor. In how much factor I can get it. Okay. But efficiency you can get maximum 1 or less than. But here, in a same case, power factor is also going to be maximum 1 or less than 1. Because phi value is going to be max to max 1. Phi is, you can say cos inverse, or you can say cos phi is going to be R by Z when Z equals to R at resonance circuit. So you can get R by Z equals to 1. At Z equals to R. Is this clear, everyone? So like we discuss about the efficiency for engine, efficiency for any particular system, in the same sense we discuss about it also. So this is power consumed for a resonance of a LCR circuit in power consumed. The resistor is the sole component in the circuit that consumes power. The inductor and the capacitor do not. Therefore, power equals to P VI cos phi, IZ into I upon RZ, and power P equals to I square R. So that is simple. Q factor of a series resonant circuit, reactive power divided by the active power, or you can say Q factor omega L upon 1. Wait. I XL upon XR, XC, why then C comes from? So that is going to be XL upon XL, L is going to be capital. XL is write it down here. So omega L upon R. I square is going to be cancelled. So yeah, this is the formula, not the previous one. So the quality factor we get this. Wait a minute. Okay. The reactive power to the active power. So this is your quality factor, that is defined ratio as the reactive power to the active power. Moving ahead, at resonance, omega naught equals to 1 by LC, Q factor equals to 1 by R into L divided by C. So this is your important formula again, or you can say frequency. Omega naught is resonant frequency. Is this clear with everyone? See, just we reversing the formulas again and again in so many different ways. Nothing more we can do here. Moving ahead, sharpness of a resonance. And in sharpness of a resonance, a important points, power in an AC circuit. Okay, let me see how much it is given. Power, resistive circuit, purely inductive circuit, purely inductive or capacitive circuit, LCR series circuit, and then question. Okay. So see, I already defined everything in the previous, like whatever need to be according to the physics or in explanation wise. Now it is written everything, and whatever the written values, we just need to look at it. Okay. Sharpness of a resonance, a slight change in angular frequency produce comparatively a large change in current when the resistance in the circuit is low than in the case when the resistance is high. See, this diagram you can copy here as well. Wait. So you can understand in a more way. Wait for a while. So that is all about discussion going on here. Okay. See, a slight change in angular frequency. This is your angular frequency. You can write in this way also. Omega R equals to 2 pi FR. Okay, resonance. So a slight change in current when the resistance in the circuit is low, then in case when the resistance in circuit high. So current is going to be changed very slightly whenever you just change the little bit value. If the value of the resistance in the LCR series is very low, then a large current flows. If this you can say at each particular condition the resistance is going to be very low because Z equals to R square. Okay, Z equals to R square plus XL minus XC to the whole square. So at which particular condition your resistance is going to be less? This total impedance when you have only pure resistor. So when the angular frequency of AC source is near to the resonance frequency, this is your near to the resonance frequency, such an LC series circuit is said to be more sharp or more selective. What is the meaning of saying more sharp or more selective? We select only this particular condition or we select only this range. Okay, and that is very small range. Is this clear, everyone? So that is sharpness of a series LCR resonant circuit. Is this clear, beta, everyone? Just type yes, and if you have any question, just type no. I mean, if it is clear, so type yes, obviously, and if you have any question, you can ask. Okay, everything is same written over here. I already defined. I'm not going to give you the diagram again. Sharpness of a circuit is measured by quality factor, Q factor. The Q factor of a series resonant circuit is defined as the ratio of the voltage developed across the inductance or of capacitance. You can put any at a resonance to the impressed value. So Q factor voltage across L or C. So here we pick L, not C. Applied voltage, which is total voltage, equals to voltage across R. So omega R L I XLI, or you can say power at L, which is XLI, or power at R, resistance, XLI, VI, VL. Mm, 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 mm. V is going to be voltage. Okay. Voltage it is, not power. That's why I'm confused. Like how it written down. VL, and then here VR is going to be IR. Okay. So in this way, I cancel omega R L divided by R. Or omega R is 1 upon under root LC. So 1 upon under root LC into L by R, 1 by R, under root L by C. At resonance, I naught equals to E naught by R. So VL equals to I naught XL, which is this. So these are some, you can say, conversion of one formula to another formula. Look at it. And these all formulas are important enough. If C or L is given to you or R is given to you, so you can directly find the quality factor. Okay, and from this, if quality factor is given to you, and see, there are four things in this particular formula number A, or you can say formula number 1, LCR or Q. So any one of the things is given to you. Okay, any three of the things is given to you, and the fourth one they ask. Simple as that. Nothing more. Either they give you quality factor and L and C and ask R. Either they give you R or C, ask about L, any particular thing. In a same sense, I naught, which is E naught by R, or you can say peak value or maximum value, and then using this particular formula, they can ask any particular thing. So at resonance, the main thing at resonance, the voltage drops across inductance or capacitance is Q times the applied voltage. So you can find that V naught, or you can say VL or VC, any particular, which is I naught XL, if I'm finding L here, that is omega L by R E naught. Clear? Because I naught is E naught by R. So in that sense, you can find these things. Nothing is changed here. Again and again, the resonant circuit, the resonance condition you need to follow, you need to use just in a way that the everything is given to you and the anything is given to you, you can use that. Nothing more than that. Okay. Whatever the things like L, C, R, V naught, I naught, L or omega naught, omega R is given to you, and according to that particular analogy, you need to find these things. Comment in electrical fence. Now, what is the importance? This is your importance. Okay, so read it. In electric fence, due to the winding of a fan, motor, coil, the L value becomes very high. Since phi tends to 90 degree, there cannot be much power consumption, and fan ordinarily would not rotate faster. To reduce phi and increase the power factor, one use a capacitor in the fence. Since for C, this frequency or this phase, this is not frequency, basically this is phase. This phase is going to be almost 90 degree, minus 90 degree. It compensates the phi due to L making phi 0 and power factor becomes 1. How so? Because phi becomes 0. So power factor, which is cos phi, gives you 1. So for a proper working of a fan, capacitor is required. Is this clear? Have you thought about it? What is the condenser? What is condenser in your this fan? What it is? Condenser. You can say a white color, cylindrical shape. What it is? Have you thought about it? You hear these words, na, like condenser is damaged or condenser is burned. So that's why your fan is not running properly. It make to the run fan fast. What it is? How it is? This is everything written over here. See, whatever written over here, this condenser, okay, condenser in this shape, na? This is your condenser. Wait for a while. Obviously not this cylindrical one. Clear? In this way, you have a condenser. So basically, condenser is a what? Condenser in normal language is equal to cylindrical capacitor. Cylindrical capacitor. Okay. And in motor, in fan, basically what it is, in fan we have so many n number of coil like this. Clear? Yeah. So this gives you, this is your inductor, this is your capacitor, condenser basically. So this gives you phi positive 90 degree ahead. This gives you phi negative 90 degree. And then adding both the things, phi gives me 0, which is power factor cos phi, which is cos 0, 1. That is everything happening here. So basically that condenser is not a condenser, it is a capacitor in general. Is this clear, everyone? You hear this terminology, na? Condenser is not working, condenser is burned out. So your fan is not working. That is not rotating. That is that. I mean, why it is not rotating, why it is not moving in great speed? Because of this. Clear? Is this clear, everyone? What happened, Vishwanath? You think what happened in this way? Don't amaze, this is going to be the cases. Sir, I have this doubt. The condenser is used to rotate the fan fast. Then it will be used in helicopter. Nice. Nice question. Why we cannot use condenser in helicopter when it is going to? Because helicopter not runs on electricity, na beta. It run on purest form of you can say fossil fuel, which is hydrogen. Not even fossil fuel. Okay. The petroleum we used in this particular aeroplane engine is going to be very, you can say, ignite or ignitiable, that produce so much energy, so it can fly the aeroplane also. So whatever written over here, na, I just make you, I just draw this. Okay, in between the, you can say, middle part of our fan, this is my coil. So this is basically when current is passing through a coil, so it behaves like a inductor. L gives me phi 90 degree. Condenser is basically a capacitor, which is a cylindrical capacitor. It gives phi phase angle minus 90 degree. So adding both of the things, we get phi 0, phase angle 0. So when we get phase angle 0, we get a power factor, which is cos phi R by Z 1. For a proper working of a fan, capacitor is required. So what is capacitor? Condenser. Okay. So importance of this, sharpness of a this thing. Q is just a number, obviously. Quality factor is also called voltage amplification factor for the circuit. If R is low or L is large or C is low, Q factor of LCR circuit will be large. That is, the circuit will have more sharpness. The electronic circuit with high Q values would respond to a very narrow range of a frequency. For a low Q values, circuit will respond to a wide range of frequency. What it is written over here? Fourth point. Did you understand fourth point? Did you understand fourth point? Fourth point can be taken or used as a selector also. Selector means uh, how many of you ever gone through a metro station where the scanning process? Everyone, I guess, right? So what is happening in scanning process? We need to narrow down the frequency range. So it can select only single person one time. Okay, what is the meaning of that? In a 2 diagram, I can show you narrow range and wide range. So this is your narrow range. This is your narrow range because range is narrow, and it is your wide range. Okay. So this is I, this is frequency, this is I, and this is frequency. So what it is? It is a narrow range frequency, or you can say narrow range resonant LCR, and it is a wide range. Resonant L. Why should I make L like C? Okay. So what it is means as you can see here, frequency range is very low. Okay. This much is this is only the range. Here you can see the range, very wide. Clear, everyone? But I don't need to say again and again. Just open your camera, open your camera, open your camera. Do you think why should I say that? I explain you guys once, I mean so many times. See, I don't want to see you, first of all. If you think you are look that much beautiful, believe me, you are not. Or if you are beautiful also, your camera quality is not. Neither mine. So why should I say this again and again? Open your camera, open your camera. What is the use for me? Even your faces distracted me. Once I see your faces, I see like I don't want to teach you guys. You are least interactive, least interested people among all the TG batches with whom I am interactive, to whom I am teaching. Believe me or not. More than you, the demo student is interactive. You are not. And your first book is going to be complete in next 2 to 3 lectures. EM waves have only 2 lectures. This is the last lecture. Still, I need to say this again and again. So the fourth point states that the electronic circuit with Q values, high Q values, this is your high Q values, would respond to a very narrow range. Okay. So this is your high Q value. Quality factor. This is your low Q value. And there is IQ value also. I don't talk about this IQ value because I go beyond the range of my limit. Okay. So, I started laughing. So this is your wide range. This is your narrow range. Like, what is the meaning of narrow range? Narrow range frequency have high Q value, means quality factor, or respond to a very narrow range. This is only a range. And for low Q value, your frequency range is going to be high enough. So it is used as a frequency selector or a particular current selector or a particular voltage selector. So whenever there is you can say touch and select system, suppose in any entrance of a mall, in any entrance of a metro, or or even in this what it is, uh, yeah, airport. Okay, in airport entrance system, everywhere when you touch or scan this particular thing, so that is the system used over there. Narrow range of frequency, only one person allowed for that particular QR code. Clear, everyone? Only one person, not whole community or not your parents or your friends. Okay, the Q value varies from 10 to 100. However, the electronic circuit dealing with very high frequencies may have Q even 200. 200 means 200 hertz. 0 to 10. This is 0 to 10 hertz. This is 200 hertz. Power in an AC circuit. Okay, we discuss this thing after a break. I need to take a break. Read this. Okay, 5 to 10 minutes break. See, in the next half, there is an important thing. Two important things we are going to discuss in a very simple way. First is LC, oscillation, and the formula and the analogy. Okay, and the second thing is transformer. This thing you already know. So after a break, I'm going to revise this thing, you guys, because this is already done. Power in AC, power formula, and then questions related to that. The important thing in this class is still remaining, which is LC oscillation and transformer. Clear? And transformer is step up, step down. That is not given in here, but I can teach you. There are only two kind of transformer. Step up means uplifting the voltage, increasing the voltage. Step down. Right now we don't use a transformer because in any particular electrical component already there is a circuit is made of. But back then we need to, or maybe you guys seen somewhere any particular voltage transformer applied to your old TV or fridge or something. Okay, so just wait for a while. Hello, hello, hello. Am I audible, beta? Am I visible also now? Hello, hello. Oh, okay. Just remove this first of all. Okay. Okay. So now we are going to revise the stuff for power and everything. And why should I look tilt? Okay. Then we are going to discuss for LC oscillation, the main thing. So even power in AC circuit, even though the average current through the cycle is zero, but that does not mean the average power dissipation through the cycle is also zero. Dissipation of electric energy is there. It's known that Joule heating effect is given by I square R and depends on I square. This term is always positive irrespective of sign of I. Okay. So power is known as your P equals to VI or equals to I square R. So that is how your power is going to be the case. So thus average dissipation cannot become zero. Let us consider a circuit that is connected to an alternating voltage source. Its voltage expression is given below. So V equals to Vm sin omega t in this way, and I equals to Im sin omega t plus phi. Like, because we have a LCR circuit, in LCR circuit the phi is going to be the crucial role. Okay, so this is your going to be the current, where Im equals to Vm by Z, and phi, this phi is a phase angle or phase angle. Phi is tan inverse XL minus XC over R, or you can write XL minus XC also, but you need to put a mode here. That's it. Okay. In this case, the instantaneous power supplied by the source becomes P equals to VI, and then putting the value of P, which is Vm sin omega t, Im sin omega t phi, and then multiplying and divided by 2. So, okay, what happening here? I just eaten up one P, which is Vm Im divided by 2 multiply by 2 sine omega t, okay, sine omega t into sine omega t plus phi. So beta, this is the formula 2 sine A sine B cos A minus cos B. Is this clear? Or you can write, uh, this is the formula 2 sorry, sine A sine B. This is the formula of 2 is not going to be here. Phi. Omega t is going to be there and 2 omega t. So this is the formula basically of cos A minus cos B. Okay. Using this formula, we can get this power formula here. Moving ahead, power formula P Vm upon Im into cos phi, and then Vm upon Im. If I am just breaking this, so Vm upon, then Vm by root 2 is Vrms, and Im by root 2 Irms, and cos phi is this phase angle, or you can say power factor. This can also be written using the RMS value of a voltage and current. So P equals to VI cos phi, where V equals to Vrms, root mean square value, Vm by root 2. Okay. In a same sense, I capital is Irms, which is Im max or peak by root 2. So this can also be written down is I square Z cos phi. Okay, because from where you can get Z, because V equals to I Z, I RMS into total impedance of a LCR circuit. Z here is again R square plus XL minus XC to the whole square under root, and capital V, capital I is RMS values. Is this clear, everyone? Clear, everyone? Till now, is this thing clear, everyone? Equation number A on this page, equation number B, equation number B on this page, equation number C on this page. Everything is clear? Which one? See, till now, this is your cos phi minus cos 2 omega t plus phi. And when you do this thing, when you solve more according to this, you can say mathematical sense. So this particular term you get Vm upon Im by root 2 cos phi. You can write, okay, this is cos A minus B. So A minus B you can write cos phi in general. Is this clear now? So this Vm upon root, okay, Vm by 2, Im by 2. So 2 can be written down root 2 into root 2, and Vm is peak value or maximum value. So peak value by root 2 of voltage divided by root 2. So it is RMS value, and cos phi is still there. So capital V, capital I is RMS, root mean square value, what we already derived in the previous classes. Okay, is this clear now? So power in an AC circuit. The above derivation proves that the average power dissipated in the circuit does not depend only on current and voltage. It also depends on the cosine of their phase angle. The quantity cos phi in this case is called the power factor. Based on the derivation given above, there three cases can be considered. So resistive circuit, purely inductive circuit, LCR series circuit. Okay, what it is means, three cases there. Either the circuit is going to be resistive circuit, so means Z equals to R only. Here two values are given. Either you have Z equals to XL, which is purely inductive, or Z equals to XC, which is purely capacitive circuit, or either series LCR circuit, Z is there. The power dissipated at resonance in the LCR circuit. So the power dissipated at resonance for LCR circuit when Z equals to R. So these are the 3-4 cases what we need to discuss, what we need to see in the above. Is this clear? Clear na? Means cos phi, because for each particular phi, when your XL, I mean Z is going to be XL, then cos phi is going to be positive 90 degree. Okay. When Z is going to be XC, then phi is going to be negative of 90 degree. What is the meaning of saying that? The phase angle between I and V is going to be in this way. Here I is going to be ahead, here voltage is going to be ahead. Here current is going to be lagging behind, here voltage is going to be lagging behind. In this, phi phase angle is 0. The voltage and the current are on a same phase angle. They are not having any particular phase angle, phase difference between them. So moving ahead, as you can see, for a resistive circuit only contains resistance. In such cases, the calculation of power becomes fairly simple because there is no phase difference between the current and the voltage vector, so that in case phi equals to 0, plugging the value of this angle in the equation, power derived above, which is Vi cos phi, Vi cos 0, Vi. So that is your formula. In this case, power dissipation is maximum. Okay. So that is power dissipation is maximum. Is this clear? Is this clear, everyone? Good. In the next case, purely inductive or capacitive. In both the cases, phi is going to be 90 degree, either positive ahead, either negative. So in this case, the circuit contains only capacitor or inductor. Either capacitor or inductor. The phase difference between voltage and current in this case will be 90 degree. So the angle phi is 90 degree. So in this case, power dissipation is minimum. So power is going to be minimum dissipated. Okay, means you get the minimum power in the circuit, in the LCR circuit, when it is purely inductive, purely conductive. So one liner note, you can write it down here. We get maximum power in purely resistive circuit. Resistive. Okay. So this is one case. Another case is this. Minimum power. Power is minimum when LCR circuit converted into purely inductive or purely capacitive. Is this clear, everyone? Because in both the cases, the phase angle, the phase angle phi is going to be 90 degree. So this is one thing. Clear now, everyone? I don't need to repeat this thing. I didn't need to explain it. Okay. Moving ahead, LCR series circuit. So this is your, again, if I make a mode here, so you can write XC minus XL also. In this case, the circuit contains all the elements, resistor, capacitor, and inductance. And angle phi in this case is given by in this manner. So this is a generalized version of the previous two cases. The power factor can be 0 or non-zero. If XC equals to XL at resonance condition, so power can be 0. If it is not, so power can be non-zero. Clear? So this is your first question. Find it down. In a series, question is, in a series LCR resonant circuit, the quality factor is measured as 1000. 100. If the inductance is increased by twofold and resistance is decreased by twofold, then the quality factor after this change will be. You need to find the Q prime. Q is given, which is R by Z if I am not wrong, and inductance is increased by twofold and resistance is decreased by twofold, 2 times basically. Tell me the answer. And quickly. After that, we have one more question, and then after that, we are going to. And quality factor is basically XL by R. Don't confuse yourself in power factor. Power factor is cos phi, which is R by Z, which is quality factor is omega L by R. Okay. So see, here itself you get the relation. Quality factor Q is omega L by R. Or sorry, omega L by Z. Z or R? R, not Z. And omega here is obviously going to be 1 by under root LC. Okay, tell me the correct answer then. I give you enough hint. B. Everyone got B? Yes. So quality factor here is omega L by R, and we use omega equals to 1 by under root LC. So Q is then 1 by under root LC into L upon R, which is going to be L by C under root into 1 by R. Okay. So L is what is given? Increase 2 times and decrease 2 times this R. So that is the correct answer. How so? Let's see that. Quality factor XL by R, omega L by R. So 1 upon R under root L by C, and Q prime R by 2 root 2 L upon this. So 2 root 2 Q becomes, and 2 root 2 Q is this. Okay. Okay, try this one. A sinusoidal varying current is applied to a purely resistive circuit. The resistance is this, and the RMS value of voltage is this. Find the power dissipated in the circuit. Very easy. I don't think more easier question than this I can give it to you. Purely resistive circuit. So I think now you can find it down the power. That much time you need for this? Seriously? Beta, see. Oh my goodness. Okay. Anyone else? C might be the correct. Seriously, you take that much time for this? Tell me the correct answer. A. Wow. Anyone else? Arey, beta. I don't think so easier than this anyone think. Power is VI cos phi. Here it is clearly written that purely resistive. So for purely resistive phi is 0. I don't know how much time I need to say this, or V equals to I. Clear? For purely resistive V equals to, or you can say I equals to what? We don't know I here, but we know V or R. So I equals to V by R. So P equals to V square by R. V is given 10, R is given 20. So 5. Array, beta. Vi cos phi is 0, this, and that is your power. Clear everyone? See, right now you are not able to solve that. And then think, even after completing the 12th class, when purely these lines are coming in front of you, now you are not able to think your questions wants to say this. So that's why I'm saying, understand that thing. Don't learn the things. Purely resistive, the line you hear, the line you see means what? Resonance circuit. What is happening in resonance circuit? Phi equals to 0, as simple as that. X equals to XL. Omega naught equals to 1 by under root LC. Quality factor is 1 by R under root L by C. I don't learn this thing. Right now I tell you because I teach you, but I know the concept. The moment I hear this resonant condition, I automatically get all the formulas in my head. Got it? Or a purely resistive circuit, or maximum current, or minimum value of Z. So many lines, so many things. They don't say resonant circuit. Never ever they write resonant circuit in questions. And that's why I give you 2-3 lines separately. If they write resonant circuit, so do you think I am going to write these 3 lines all together? Like maximum current, minimum resistance, and so and so. They don't write. Believe me on this. And never ever you get question like this one even. Okay, now what LC oscillation I already defined in the previous class a little bit. So see what happening here. Suppose I apply a voltage here, alternating voltage here. Okay, this is your alternating voltage. I apply alternating voltage, which is V equals to Vm sine. If it is positive here, so current is going in this way. Okay. I. Now you can see that The moment current is going in this way, first of all, it is going to be create a induced EMF. Clear enough? And when this going to create a induced EMF voltage XL, so obviously this going to get the whole of voltage in this. Okay, means whole of your this voltage is going to be deposit here, which is VL, which is VL. Okay, this is your VL. Now this VL is going to be discharged over here. But the moment this is going to be, this voltage is going to be charge this capacitor. So here what do you get? VC. Clear? This is your VC. But the meanwhile it is charging, it is going to discharge again. And in discharging, it flow a current positive to negative, and this again going to charge. I mean this again going to make a current in this way, and then it is going to give you induce EMF, develop a voltage here, again produce a current, and then it is going to charge. So it is charge and then discharge, charge and then discharge, charge and then discharge, charge and then discharge. So this behave like this. Suppose I initially it is this mean position, right? I make a circuit in which L and C apply, and this is what I am doing. Here I apply your voltage. The moment I leave this, charge, discharge, charge, discharge, charge, discharge. So current behave like a pendulum or a spring mass case in simple way. Okay. In both the cases, how it is, I mean, analogous to this case, first of all, understand this. How it is. Oh my goodness. Wow. Wait a minute. So how it is analogous to this circuit? See, suppose, yeah. Okay, just a minute. Like I mean, like in this particular circuit, I apply this particular voltage Vm. In a same case, this is my spring mass system. Okay, this is a spring attached, and this is a mass attached to this spring. This is a mass attached to this spring. The moment I apply a force in downward direction, okay, either in a downward direction or either in upward direction, either I extend this spring, okay, suppose this is your spring, either I extend this spring, either I compress. The moment I leave this, it is going to give me the frequency, or you can say basically oscillation in this manner. Okay, is this clear now? Means up, down, 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 up, down. In a same sense, charge, discharge, charge, discharge. First of all, it is going to charge. Then here, discharge. And then give you current. Then it is going to give you induced EMF. Okay. Then it's going to give you the current, and then charge, discharge, induce EMF, charge, discharge, induce EMF, charge, discharge, induce EMF. So this cycle is going to be, and that particular thing is known as your LC oscillation. Oscillation is basically what? In between the energy of a capacitive energy, which is half CV square, half QV, or half Q square by C. Okay. Or in the energy of a inductive energy or magnetic energy, which is half Li square. Clear? So this continuation process is going on. Obviously, it is going to be dissipated. Dissipated in what form? In a heat form, in another current form, and so and so. So that thing we need to find. So what is a LC oscillation then? Charge variation in LC circuit, Q equals to Qm cos omega naught plus phi. How we get this? As we know simply, what we know basically, I equals to dq by dt. So if I need to find the charge, so I need to integrate, and I is sine omega t, and the integration of sine omega t is nothing but cos omega t. And basically this qm is all the integration we done in the previous class. So q equals to qm cos omega naught t plus phi naught, where q is the charge in the circuit at any particular time t. Qm is the charge in the circuit at initially, and omega naught is 1 by under root LC natural frequency, and phi is phase constant. Okay, this everything we know. Moving ahead, how it is doing LC oscillation. First of all, you need to know the similarity between this. So similarity between electrical and mechanical oscillation, the LC oscillation is similar to the mechanical oscillation of a block attached to a spring. Again, this thing, there is a spring. Okay, there is a spring, and if you attach a block or a mass m, okay, or you just tilted this, so it is starts doing this way. So oscillating with frequency omega naught, this is your equation. What is this equation? Initially it is have x, and after tilting x naught. Okay, and then you give the displacement which is x. So with this displacement there is simple equation f, which is ma equals to minus of kx. Okay, and a is d square x upon dt square. So when we solve this equation, wait a minute, when we solve this equation, we get this equation. Okay, this one. So d square x upon dt square omega naught x square x, where omega naught square is nothing but k by m. Okay, omega naught is under root k by m. It is not, or rather you write in this omega naught square k by m. K is a spring constant. So x correspond to q. Here x correspond to charge. In case of mechanical system, F equals to ma m dv by dt, m d square x by dt. For an electrical system, E equals to L di by dt, or I is d square q by dt. So comparing these two equations, we see that L is analogous to mass. L is a measure of the resistance of change in current. In case of LC circuit, omega naught is 1 by under root LC. As you know this. Okay, this is. And for mass of a spring, omega naught is under root k by m. So 1 by c is analogous to k. The constant k is f by x, or you can say f equals to kx, when external force is required to produce the displacement, where 1 by c equals to q by v, as we know this. Q equals to cv, simply. So from here 1 by c equals to v by q. Capacitance, charge on capacitor. Tell us about the potential difference required to store on a unit charge. Okay, so in this way, wait, you don't, okay, in this way you get the equation which is simple. I can give it to you. The equation basically d square q upon dt square plus omega naught square, and q obviously equals to charge. Here omega naught square equals to L by C. Okay, and no, wait, 1 upon LC, and omega naught equals to 1 upon under root L by C. So here 1 by C behave as a K. Okay, 1 by C, and L is behave as a M. So here you can write it down. L is analogous to mass, means conductor is analogous to mass, and 1 by C, not C, is analogous to spring constant K. Spring constant. Rest everything is same. Like in this scenario, this is going to be oscillate. Here the charge is going to be oscillate, because okay, one more thing. X is analogous to, here not X, we are writing charge is analogous to displacement X. Is this clear, everyone? So in this way, this LC oscillation is important, and this is the meaning of LC oscillation. I think from boards it is omitted, but in any particular case, if you get LC oscillation question like this, so obviously natural frequency in LC circuit is under root 1 by under root LC omega naught. That is the same case, same scenario for this particular thing like LCR circuit. But this is the magic, or this is the meaning of this LC circuit, oscillation. Is this clear, everyone? Clear bit, everyone? Okay. So now find this. An LCR circuit contains this much inductor, this much capacitor with an initial charge this. The resistance of the circuit is negligible, obviously R. What is the natural frequency of the circuit? You just need to find the natural frequency. L is given, C is given. Tell me. And then we are going to discuss about transformer. Tell me. See, L is given. L is given, which is 20 millihenry. And I think you know about milli and micro. I'm not going to write. 50 micro farad. Okay. You need to know, you need to find omega naught. Nothing more than that. Natural frequency, na? Natural frequency. You know the formula. And just calculate and tell me. See, it is omitted from the CBSE whole soul. If it is not, so that is very important derivation and everything. But I don't think so in your term it is going to be given in any particular entrance exam also. Because like we have a force or damped oscillation in mass system, here we also have a, you can say forced, or you can say when voltage is given higher or higher, so that is used as a force. Okay. D. Okay, let me check. See, I don't even know the answer. But the answer is not D. Frequency they ask, beta, not omega naught. See, it is if V given, na, so you need to use your brain a little bit more. First of all, you need to find this. And from here, there's a relation omega naught is 2 pi V or F. So frequency they ask, not angular frequency. This is your angular frequency. And this you need to find. Oh my god. See, even the answer is not correct mentioned. One is missing here. Okay. Sorry, my bad. Here one is missing. So the correct option is first. 159. Exactly. I remove this whole. Great. The correct option is 159.24. 24 hertz, and you need to use this. Okay, how so? Exactly, option A. So all units in SI natural frequency, so V equals to 1 by 2 pi under root LC, because so using this you can get this. Omega naught is 1 by under root LC, which is 2 pi F. Okay, so you need to find this F. So F is 1 by under root 1 by 2 pi under root, this is 1 by LC also. Okay, from here frequency is 1 upon 2 pi under root LC, 1 upon, or date. This is your case. Okay. Now working principle of a transformer. First of all, what a transformer is. Okay, you have seen the transformer in right now also. In your nearby park or in your locality, there is a transformer, right? You hear this terminology in summer days, like transformer is burnt out. So light is not going to come for 2 days or for a day or for half day. So what does transformer do? Tell me. You have seen transformer in your roundabout, near to your home, in any park, or near to any particular electrical pole from which you get the electricity. So what is that? Tell me. Transformer is basically an instrument which is going to they increase or decrease voltage. Exactly. Transformer the current to transfer the current to various places. No, beta. They increase or decrease the voltage. See, whatever the voltage, whenever we need to transfer current, basically alternating current and alternating voltage. So we need to step up, or we need to, you can say, increase the voltage to transfer that particular current or voltage altogether. But obviously, if 11,000 voltage is coming in your home, so every you can say electrical appliance is going to burn out, because they only work on 220 max or 240, right? Isn't it? Because 240 is peak value, maximum value. Average value is, or RMS value is peak or maximum value by root 2, even less than that. Clear? So if that much voltage is coming in your home, so every appliance is going to burn out. So basically what the transformer do, from power station to in your locality, in your nearby street, nearby park, the transformer is set up, and from big power station to your city or locality power station, from your locality power station to your pole, in this way they decreases the voltage. Clear? So either they decrease or either they increase the voltage, not transfer the voltage. So working principle is very easy. First of all, transformer look like in this way. There are primary coil, NP turns, initial voltage, initial current, secondary voltage, secondary turns. If as you can see, this is step down. What is the meaning of step down, step up? Step up, okay. There are two types of transformer. Step up, increase the voltage. Second, step down, decrease the voltage. Okay. I'm just going to write increase or decrease. Increase, increase or decrease. Where? On secondary coil. Obviously, you can see that the number of turns on primary is higher on the secondary. So it is step down. This one is, I can write here, this one is step down. Okay. Basically, in your locality, in nearby park or on the pole itself somewhere, you have seen the step down, not step up. Step up is basically made in power stations. Okay. So working principle we are going to see in the next, but transformer is basically a device which is going to increase or decrease the voltage coming in this way. Clear? Two types, step up, either increase, or step down, either decrease. Like part of a transformer: core, winding rings, insulation agents, tank, transformer, oil, oil conservators, breather, radiators, and fans. These are, that is not, you need to worry about all the things, because the this construction is not there in any kind of questions right now. Working principle, that is important. Let's look at it. So what is working principle? According to Faraday's rule of electromagnetic induction, this alternating flux links the transformer primary and secondary windings magnetically and generate EMFs E1 in the primary winding and E2 in the secondary winding. Then the EMF E1 is referred to as the primary EMF, while the EMF E2 is known as the secondary EMF, where EMF in the first is minus Ny d phi m by dt. Okay, simple this. N1 how much? And d phi m. Phi m is what? Magnetic flux. In the same, wait, where is that? Okay, wait. I need to select. I cannot. I need to beta copy this to make you more understand. I can paste it down here. Okay. Then I can select. And then can I move here and there? I need to shrink it down. So as you can see, this is, yeah, perfect. Okay. And now I can, yeah, beautiful. So as you can see here, this is the EMF on the primary turn N1, and that is maximum, or you can see more. So obviously when N1 is greater than the secondary, so it is step down. And for step up, initially primaries need to be less. So that is your step down. So this is your flux generated on this particular slide. I'm saying this particular side. Here, E2 is minus N2 d phi m by dt, dividing the above equation. Okay, equation number 1, equation number 2. This is your equation number 1. This is your equation number 2. So in both way, the flux is going to be equal. D phi, I mean change of flux, basically, not flux in general, but change of magnetic flux. Change of magnetic flux is equal in both the way. So this induced EMF is directly proportional to what? Number only. E1 by E2 is N1 by N2. Okay. So if we know the E1 and if N1 by N2 equals to E2. Clear? In this way you can, in reverse way you can find E2 because we need to find E2 now. So from here, E2, or you can say EMF, voltage on the secondary coil, you can write S or N also. How you can find better? That is N2 by N1 into E1. So obviously, if N2 lesser than N1, so it is less than 1, so your E2 is lesser than initial. Means voltage on the secondary is obviously lesser than the primary one. Because here N2 by N1. If I reverse this condition, so it becomes step up. Is this clear, everyone? Is this clear, beta? Here on this particular screen, I can show only, I can see only 1, 2, 3, 4, 4 students. But in this particular thing, I can see 9 students. What is this? Ayal Netra, Parikshit, Dakshin, Darshan, Pavan, Dharmeshwar, Darshan K2, and so and so. Where are you guys? Is this clear, everyone? Good. Okay, so ideal transformer, what it is? An ideal transformer is purely a theoretical transformer that has no loss at all, including no core loss, copper loss, or other transformer loss. This transformer is thought to be 100% efficient. Obviously, that is why it is ideal. Okay, what is copper loss or transformer loss and so and so? See, yeah, as you can see, these basically wires are made of copper. So there is a copper loss, and in this particular flow, there is a current is going to be generated in a swirl, and that particular current, what is a swirl first of all? Like you have seen in a water, in a flowing water, there is a this kind of circulation is formed, And whenever you put a leaf or any particular stone, so that is going to be in the center. So in the same sense, when this particular flux is generated, when flux is going to be from this end to this end, so in a swirl kind of condition, there is a current going on. And that current is known as eddy current. Is this clear? Is this clear, everyone? What is eddy current? In you can say when this flux is going to transform from initial or primary to secondary, there is a current is going to be in this way. Well, I don't know how to, that is, if I'm not wrong, this word of this. Okay, like there is a water flow. In water flow, you can see na, in flowing continuous water, there is a this kind of formation you can see. Okay, turning around like a tornado. So in this way, current is going to be, that is known as an eddy current in general. So obviously there is going to be so many losses. First of all, due to copper, due to core. I mean, this particular metal is made up of something, this. So due to a core also, and so many other losses. So any particular type of transformer in which no loss is going to be, that particular thing is known as ideal transformer. Moving ahead, EMF equation of ideal transformer. So EMF equation of ideal transformer, we are going to find it down, and that is very easy. Primary winding, secondary winding. So EMF equation of ideal transformation, that is primary current IP, number of turns NP, voltage at primary VP, magnetic flux phi, transformer core, number of turns secondary, we can say secondary current IS, voltage secondary IVS. So the induced EMF or voltage ES in the secondary with NS, number of turns in the secondary, calculated is in this way. This is your first equation. And in this way, this is your second equation. For an ideal transformer, EP equals to VP. Now what it is? Induced EMF is going to be equating for voltage at primary coil. In the same way, by approximation, if the secondary is an open circuit, then the current drawn from it, the modest, or you can say for ideal transformer, the induced EMF at the secondary coil is equal to the voltage at the secondary coil. So calculating this, Vs equals to minus Ns d phi by dt, Vp equals to minus Np dp by dt. So these are your important equations. Important equations. And then this one is most important. So from equation 3 and 4, Vs equals to Vp equals to Ns by Np. The above equation is known as the transformer equation or transformer formula. Very important. Simple, very basic question you get from this subtopic in the same way. Nothing more than that. Okay. These are four things. Among the four, you get three things in your hand in the question. Like number of primary turns, number of secondary turns, or voltage at primary. So you need to find voltage at secondary or reverse. Or sometimes to make a question a little bit difficult, how they can formulate the question, like the voltage is going to be drop 90%. Okay. So obviously when voltage is going to be drop 90%, so what is the meaning? And Vs is secondary 90% of Vp. Okay. In this way, so when you know the relation between Vs and Vp and 90% of, now you get the relation between Vs and Vp. Okay. Which is Vs is 0.9 of Vp and you get Np. So you can easily calculate Ns in this way. Suppose Np here is 1000. So in this way, you can find the number of turns on the secondary. Is this clear? And in class assessment, in maybe homework, this kind of question I given to you guys. So don't worry. Okay. Simple, this formula number 5 is very, very important. And based on this, you can get if you are lucky enough, directly one question in JEE mains also. Is this clear? Okay. Clear everyone or not? Okay, good. Moving ahead, turn ratio. This is known as your turn ratio. So the turn ratio is measured to determine whether the secondary coil of a transformer has more or lesser windings than the primary. The number of windings on a primary coil is equal to NP, while the number of windings on a secondary coil is NS, representing the number of turns. IP Vp equals to Is Vs. This is your one equation. Combining equation 6th and 5th. So IP by Is equals to Vs by Vp. Now this is the glitch here. Now this is the main thing. See, just understand this. Ns upon Np. This is the number directly proportional to Vs upon Vp. Clear? Is this clear or not? And is this correct or not, first of all? Yes. Okay. What it is, as we know, Vs directly proportional to number of turns. In the same way, Vp is directly proportional to number of primary. So if I'm dividing equation 1 by 2, so I get this, or reverse of this. So most of the time what happen, instead of voltage, they give current. And what you guys do, the wrong thing there, IP upon IS equals to NP upon NS. Wrong. Why? So obviously we know V equals to IR. Clear? So if we know the V, so I can be, or V by R in this way. So here primary divided by secondary is going to be NS. Wait. Yeah. So what? Okay. Instead of saying wrong, NS by NP. That is the wrong thing. Because I don't know why maximum number of students do this mistake, silly mistake. Like V is IR, so if Vs by Vp is Ns by Np, so in same case Ip upon Is going to be Ns by Np also. Is this clear? Is this clear, beta? Okay, so that is the scenario. You just need to use this. So either current is given, either voltage is given, either the relation between current and voltage for primary to the secondary, you need to use this to find the turn. So this is your important again, turn ratio. Okay. Now efficiency, sometimes they ask this also. So efficiency, power output to the power input, power output divided by the power input plus losses into 100%. So efficiency, power output minus losses divided by power input into 100, which is 1 minus loss upon input power into 100. Okay. This particular formula they don't sometime ask, not usually, but efficiency is not asked in transformer. So now this one is your question. A transformer primarily winding is powered by this AC source. Turn ratio is this. Turn ratio. K basically, okay. Wait. Instead of this one is important. Turn ratio. Okay. So directly you can use this. Vs by Vp is turn ratio, K. So here K is given. Turn ratio. Okay, which is 10. And what is given? Primary voltage, VP, 120. D, exactly. See how easy it is. Clear, everyone? Is this clear to you? Kyle, beta. Clear na? See, turn ratio is given, primary is given, and we know always and always VP upon VS, which is turn ratio is always and always going to be in this way, NP by NS. So that is directly multiply okay, turn ratio. Here turn ratio is given in the opposite sense. Then you can find this. Okay, because using this, if you divide, so 12 is not given in this list. So the obvious thing is VS by VP is given. And that is NS by NP, which is 100. So VS is VP into 10. Clear na? Remove this thing. D. V2 by V1, N2 by N1. N2 by N1 is the turn ratio 10, and you can find this. Okay. A transformer has that much turns in primary coil and 8 ampere current flows through it. When the input power is this and the output voltage is this, determine the number of turns in the secondary. See, input power is given, current is given, so voltage is given. Clear? Input voltage, output voltage is given, primary turns is also given. So you need to find the secondary. I'm not helping you in any case in this. Find this. That is very easy. Number of turns. And then we are done for this class. And then you need to do this. Oh, good. Wait. Where I throw the pen. Everyone got C. See how you get C. Consider the case of an ideal transformer, or you need to P in equals to P out, which is 1000 watt. P out equals to VSI. Now the current through the secondary circuit is IS, which is P out upon VS, 10 ampere. So either you in this way you can find. So IP upon IS, which is NS upon NP. Okay, in this case NS into wait 800 tons. Either you get in this way IP. Okay. See, one scenario is there. VP equals to VS for ideal case. Okay. For ideal case, it is going to be something for ideal transformer. For ideal transformer case. Okay. Then IP into R equals to from here what we get, VP upon VS equals to 1, and VP by VS basically VS is nothing but NP upon NS. Okay, and then IP. So if I do this, IP by, how can I get this relation? IP, okay, primary is upper, na? So IP upon IS, which is 8 by 10, and then it is going to be, how we get this relation, because I'm confused in this. IP by IS equals to NS by power VI. Okay. Got it. When you multiply V and I both together, so you get this relation IP into, instead of Voltage is not equal, power is equal. For ideal case, wait for a while. Here I can make. See, for ideal case, power on primary equals to power on secondary. Power is basically wait, Vp into Ip Vs into Is, right? So Ip divided by Is equals to Vs divided by Vp equals to Ns divided by Np. So in this sense, I get this relation. Is this clear, everyone? See, I confuse also. So for ideal case, that is the important formula also you can use. Is this clear, beta, everyone? Okay. For normal cases, IP, IP divided by Is is going to be the same because using V equals to IR. But for ideal transformer, power is going to be equal. So IP by Is is going to be reverse case. And then in this way, you can find Ns equals to IP by Is in this. So that is how you can find 800. So in this way, we finish this. So this is your chapter done. In the next class, we are going to discuss about Friday class. Yeah. DRS of this particular chapter. DRS means what? Chapter assessment. So what important thing we done in this class? Resonance, sharpness of resonance, power in AC circuit, power factor, LC oscillation, and principle of transformer and its all derivation.